Hello folks, today in this video we're going to talk about electrostatics, the science of charges and forces and what's happening in the electrical world. We're going to take a look today specifically at where charge comes from as well as the force between charged particles. Let's go ahead and get started. So first up, where does electrical charge come from? Well, charge is one of those fundamental things about our universe. Just like you can't be like, well, where does mass come from? Mass is just something that exists in the universe. The same thing with charge. You can talk about what particles carry charge and ultimately the little fine details, but where charge comes from is just something we have to accept. Charges exist. Now, our fundamental particles are force or charge carriers. Typically, we consider our electrons and protons. You guys probably remember from your chemistry courses that electrons exist on the outside of the atom, and those are negatively charged. And then inside the nucleus of the atom, you have protons and neutrons. Neutrons, being neutral, carry no electrical net electrical charge, but then protons, they do carry a positive charge there. Now, there are little details that protons are made of smaller things, but we're not going to worry about that for this course here. Now, one thing you might not have considered before is the fact that it is not a coincidence. The electron and the proton are negative and positive. They also have the same value of the charge, though, and that's actually really important. That helps with so many things in constructing our world and the chemistry that we live in here, that the electron and the proton have the same magnitude of the charge, and we call that magnitude the elementary charge. So the elementary charge is the amount of charge that either a proton or an electron has, and it's measured in a unit called coulombs, which is abbreviated capital C. So COULOMB. Yes, coulombs. And it just so happens that one electron or proton has a magnitude of charge of 1.602 times 10 to the minus 19th coulomb. So not very much. The reason why they're, can do things then is because we have a lot of electrons and protons. And so those will add up to a large charge difference. So that's where charge comes from and what things carry charge here. But I want to take a look now at the idea of the quantization of charge. Because there are charge carriers, you actually can't have any particular charge you'd like on an object. You can only have whole integer multiples of these elementary charges. So we say that the amount of charge in an object is quantized. Quantized meaning it can only take on certain values. So I couldn't have 1.5 electrons worth of charge on something, because you can't transfer half of an electron from one place to another. That's what we mean that it is quantized. So it has to be a whole integer multiple of that elementary charge on that there. And we'll take a look and see what that kind of looks like for us here. But a few practice questions here. It says first, how many excess electrons are on a sphere with a charge of 6.2 times 10 to the minus 6th coulombs? Well, one thing you can do, you can use that elementary charge value as sort of a ratio, or if you really want to go crazy, you could do stoichiometry if you're thinking back to chemistry there. So I know that there are in one electron, the value is 1.602 times 10 to the minus 19th coulombs. And what I'm asking is how many electrons, X, will give me a charge of 6.2 times 10 to the minus 6 coulombs there. So all I have to do then is go ahead and solve my ratio there, and I get a value, it looks like, of 3.9 times 10 to the 13th electrons. Then what is the charge of a sphere that has 9.7 times 10 to the 4th electrons removed? So here I'm going backwards. I still know that same ratio. One electron is 1.602 times 10 to the minus 19th coulombs. And I want to figure out, okay, what's the charge of 9.7 times 10 to the 4th electrons? And so again, just solving out this ratio there, I end up getting a value of 1.6 times 10 to the minus 14th coulombs. Now you notice I put a positive charge here, or a positive value. The reason I did that is because this has had electrons removed from it. Because electrons are negative, this sphere must then be positive because those electrons have been removed. Okay, and then now thinking about that quantization of charges, which of the following charges is not possible for an object? So these are very small charges, just to kind of get the point across. But the idea is that this has to be some integer multiple of the elementary charge. So if I take a look at this, I can clearly see 3.02 times 10 to the minus 19th. That is definitely 2 times the elementary charge. That's 2 electrons, because 1.6 times 2 is 3.2. So what you might do is you might go through each of these and divide each one by the 1.6 times 10 to the minus 19th and see which one doesn't end up being an integer. And it looks like if you do that, that one is 5 electrons. And I believe this other one, I actually didn't do the math myself. Let me do it now. I believe it's 7. Yeah, that's 7 electrons. And so then this is the only one. If you divide 4.4 by 1.6, it does not come out to be an integer. So that charge would not be possible for an object to have, because you could not transfer that amount of electrons. Okay, let's talk now about ways to charge up an object. Well, first, objects are made of tons of different materials. And in general, we can kind of classify materials as one of 2 things. They can either be conductors or insulators. Conductors allow for the easy flow of electrical charges. Insulators, as I'm sure you've heard of, resist the flow of electrical charges. This doesn't mean that insulators you cannot conduct a charge through. You definitely can. If you put enough of a force behind those, they will go through, but they resist it more than a conductor will do. Conductors allow for the easy flow of electrons there. Now, there are, in general, a couple of different ways that you can charge up an object, and we're going to take a look at those in some activities and labs that we can do. But in general, they fall into one of 3 categories: friction, conduction, or induction. Friction is by far the simplest one. You have probably done this before, whether you rub your shoes across the carpet or you rub a balloon on a sweater or something. Friction can transfer electrons from one object to another. You're literally ripping off the electrons from one object onto another object. So friction allows you to transfer from one to another. When you do frictional charging, you always make one positive and one negative object. And we'll talk a bit more about why that is, but it has to do with the fact that you can't destroy or create charge out of nowhere. So friction always makes one positive and one negative object, because you're transferring electrons from one to another. Once you have some object that is positive or negative, though, you can then do charging by conduction or contact. Literally, the idea is that if you have something that is negative, let's say here we've got this rod, and it looks like that rod is negative, you could just touch it to another object, and that object will then gain that charge, and then you'll have 2 negative objects. So conduction makes objects the same charge, typically. If I have a negative rod, I can then make a negative sphere, because I can transfer some of those electrons from one to the other. Then you've got the weirdest one, induction. Charges are removed or added to an object via a ground connection. So it's good to talk about, what does a ground actually mean? Well, it comes from the fact that there's the ground below us, that the Earth is a great sink or a great supply of charges, particularly electrons. So if you have an object that has a bunch of charges on it, those charges repel each other. They don't want to be near one another. So if you give them a pathway to flow to a bigger object like the Earth, they will take that connection. And so we call that a ground connection. Well, you can use the fact that the Earth is so large and has so many charges on it to either add or remove charges from an object. So it might be a little hard to see. I think my video is in the way here, so I'll try moving it a little bit. But you can see, moving on, going back, that what they do here is they have a negative rod and they bring it close to a sphere. Now this sphere becomes, very importantly, polarized. What does polarized mean? Polarized means that the charges have moved in order to create one positive end and one negative end. Because this rod is negative, it's going to push the negative charges away from it. And so you end up with one side positive and one side negative. Now this sphere is still neutral overall, right? It doesn't have any more or less protons or electrons. It's just that overall, it's going it's just that some of them are on one side and some on the other. But here's what you can do. If you ground the one side of this sphere, those electrons are too close to each other. They would much rather be further apart. And so if you give them an opportunity to go somewhere else, they definitely will. And so then you can actually force them to go into the ground. And then if you cut that grounding connection, I have now made a positive sphere. So one interesting thing about induction is induction allows you to make objects the opposite charge by utilizing that grounding wire. And we'll go ahead and take a look at this in an activity to make sure that things are making sense there. Okay, so what is kind of behind all of this, like charging by conduction or induction, is this underlying principle that charge has to be a conserved quantity in our universe. Like many other properties of matter, like momentum or mass or energy, the total number of charges in any system must stay constant. You can't create charges out of nowhere. So when two objects interact, they're neither created nor destroyed, but they're always transferred from one to another. And I'm going to add one other kind of corollary to this, is that typically only electrons can be transferred. When we are charging up one object or another, we are always talking about the movement of electrons, simply because they're on the outside of an atom. You couldn't, rip the protons out of an atom and transfer it from one to another. It's much more difficult to do, and that would involve some weird nuclear physics that we're not going to get into. So when we're saying they're transferred or moved from one object to another, we're talking about electrons. Okay, last thing with charging an object here, I've got an example. It says that two spheres, A and B, represent identical metal spheres with different charges. If the two spheres are brought together and allowed to touch, the first question is, which sphere will gain electrons? You can think about this one a couple different ways. My favorite way to think about it is just which one has more electrons right now. Clearly, the negative one is going to have more electrons. So when they touch, it has to be that the one with more electrons will give them to the one with less electrons. That's always going to be true. And so that's the way I think about it. And so then I know it's going to be sphere B that's going to gain electrons there. Then it asks, what will the charge of both spheres be after they are separated? Moving my screen back over there. To figure out the charge after they're separated, we have to use the fact that these two things are conducting. And so they are going to want to become equally charged afterward. Now, this is a very specific type of problem that you'll see come up. And you could almost just memorize that anytime you want to find out the charge after two things touch, you are going to take the average. So what I would do, go ahead and take those two charges, add them up, negative 1.6 times 10 to the minus 6th coulombs plus 1.0 times 10 to the minus 6th coulombs, and then divide by 2 because there's two spheres. So just average them up. Do make sure you take into account the signs, that one's negative and the other one's positive. And then when I do that in my calculator, I got negative 3.0 times 10 to the minus 7th coulombs. So we can see sphere A went down like we would think because it would be losing electrons, so it's less negative. And then sphere B got more negative to negative 3 because it gained those electrons there. Okay, one last concept for today here is the concept of electrical force. And the name we give to the electrical force is we call it the Coulombic force, or Coulomb's law. Coulomb's law describes the electrical force of attraction or repulsion between two charged particles. This force has a few different things that go with it. First, it increases as you get the charges to be greater. The more charge there is, the greater the force of either attraction or repulsion. Next, it decreases with the square of the distance between the objects. This is a key point here, that this bottom term has r squared in it. You might have seen an equation similar to Coulomb's law before. That is Newton's universal law of gravitation, the fact that the force of gravity between two objects depends on their masses, and then the distance between those two objects squared. For charges, it is very similar. Now, getting into the kind of the meat of this equation here. So this is my Coulomb's law, and it's K Q1 Q2 over R squared here. K is what's called Coulomb's constant. It is just a number that's on your reference table, and it's 8.99 times 10 to the ninth Newton meter squared per kilogram squared. Quite a large number. This explains one big thing, which is that gravity, if you look at big G in the gravity equation, it's 6.67 times 10 to the minus 11th. It is much, much smaller than the electrical one. This is why electrical forces in general are much, much stronger than gravitational forces. It's why you can have an attraction or repulsion between two little teeny spheres. For gravitation, you wouldn't measure anything between two little spheres. You would need to get into the size of planets before you could actually measure a force of gravity between two different things. Next, you've got Q. Q here is just the charge of the two objects. And you should take into account the positive and the negative. It can help you kind of know whether it's attractive or repulsive. If the two charges are the same, no matter what, whether they're positive or negative, you will end up with a positive force. And that positive force will then be repulsive. And so they will repel each other like that. If the two charges are opposite charge, doesn't matter what they are, they will end up being negative. Or the force will end up being negative, and therefore it will be an attractive force. So Q is my charge, and we typically measure that in coulombs. And then lastly, R. R is one of the most confusing things. We call it R, but it's not a radius. It is simply the distance between the two objects. So this distance right here between the center, technically, of both of my objects, and we typically measure that one in meters. Okay, so let's go ahead and take a look at an example of coulombs here. It asks first, what is the electrical force of sphere A on sphere B? Wants both the magnitude and the direction. So for sphere A on sphere B, we're thinking, okay, what's happening to sphere B because of sphere A? Coulomb's law is that it's K Q1 Q2 over R squared. So we'll plug in our K, 8.99 times 10 to the ninth Newton meters squared per Coulomb squared, times each of the charges, negative 1.6 times 10 to the minus 6 coulombs, times 1.0 times 10 to the minus 6 coulombs, and divide by that distance on the bottom, which is 2 meters, and then do not forget, of course, to square it. Solve that out in your calculator. I end up getting negative 0.0036 newtons. So there's a few ways you could answer this. Magnitude, of course, just means the size of this number. So the size I've got, 0.0036 newtons. The direction, this negative tells me it is an attractive force. Makes sense. One positive and one negative. And so that force, you could say it's to the left. You could say it's towards sphere A. You could even put the negative as long as you've kind of defined it that, okay, yeah, it's going to be that way. And that makes sense there. Then this next one asks, what's the electrical force of sphere B on sphere A? There's a few different ways you can think about this. And I want to go back and just take a look at that picture one last time on the previous slide, which shows you that these two forces, there's F1 and F2, are equal to one another. So remember from Newton's third law back from physics 1 that the force of one object on another is equal to the force of that second object on the first, that there must be equal and opposite forces. So if sphere A is pulling sphere B with negative 0.0036 newtons, then the magnitude of sphere B on sphere A must also be 0.0036 newtons. The one key difference here is the direction, right? If this one's pulling to the left, then this one would be to the right, because that force would then pull that way, and that would make it both attractive. Okay, folks, that's it for charges, types of charging, and forces of attraction. Thank you guys so much for watching. Have a great rest of your day.